Welcome to this short video on matrices and computer graphics. And actually, I already messed up. This is really just a look at matrices and web graphics. Okay, computer graphics is even larger. We're going to look at how matrices are used throughout web graphics. We're going to learn about these things called homogeneous coordinates. Okay, and we're going to apply transforms to 2D graphics and text. Okay, and see that these things apply to 3D graphics as well as 2D. The web technologies we're going to be using here is HTML, is what we write web pages in, CSS, what we style, a language for styling web pages, and something called SVG, Scalable Vector Graphics. It's a language used on the web for 2D graphics. Okay, let's take a look at those things. First, remember, if I say don't click this, don't click this. Okay, that's a bad thing to do. Don't click that. Oh my gosh. So this is HTML. Okay, it is just plain text. This is syntax highlighted for programmers. Okay, if I write this out, okay, and then look at it in a web browser, this H1 weird little squiggle becomes a heading. These P, the stuff within this P block, becomes a paragraph. So if I want to see that, let's click this example file. Oh, welcome to HTML. I can write a paragraph. Okay, seeing this is my web browser, nice and simple. No styling. Okay, if we want to style this, oh, I'm getting seasick. Okay, if we want to style this, we use something called CSS, Cascading Style Sheets, and it looks something like this. We can put it straight in our HTML. It says, oh, the body, make the background color something. Center, the heading, make the background color yellow. Oh, let's just take a look. Okay, so we can add style. I didn't say this was pretty style or nice style. I just say we can add whatever style. The quality of your styling depends on your artistic ability. I do not have any. I think I'm going to get sick. So I warned you, don't click this. What do you think that was doing that? I guess we're going to see. Now, similar to HTML is something called SVG. Instead of starting with HTML at the beginning, we say Scalable Vector Graphics. By vector meaning, these aren't images, okay? Those things like cell phone pictures are what we call raster graphics. This is vector graphics. We have things like rectangles, polygons, text that we just specify with a language that looks kind of like that HTML weird stuff that we saw, okay? We can render that right here in our browser. It works with browsers. That's what it was designed for. And we get to see these different things, okay? Rectangles, circles, polygons, and such like that. Now, HTML and SVG, they might try and hide this a bit from normal users, have coordinate systems, okay? And the coordinate systems, for those of us who have been doing math all our lives, drive you crazy. Because notice, X goes the way we're used to, but Y increases down, okay? Why do they do that? Because HTML was designed for documents. Documents keep adding stuff as you go further and further down the page. So they made Y increase down the page, not up like we're used to with all our graphs, okay? Just have to get used to it, okay? Now, what might we like to be able to do with our graphics and other things? We'd like to be able to scale things, make things larger, right? That's built into our browser a bit, right? We can make things smaller, we can make things larger, right? That's just built right into their browser. How do they do that? Okay, scale. So that could be growing, shrinking, you might call it zooming. Rotating. Okay, we're used to rotating. Okay, our cell phones know how to rotate and all sorts of things. Translate, pan across a large map, and more. How do we do this? Well, you already learned about this because you're watching this video, so You learned about this in your math class. You learned that it's done with matrices. You go from an old coordinate system to a new coordinate system by multiplying by a matrix, okay, and adding a vector, okay? Matrix multiplication can do all sorts of things. All the scaling, all the rotation, things called skew or shearing and stuff like that. But then we have to add this extra bit so we can translate, so we can move it someplace. Okay? That extra bit is a pain to deal with. Okay? So we got a trick for that. Okay? Basically, we want one matrix to rule them all. There's something called homogeneous coordinates, and they add a dimension, okay? And this has deep mathematical significance with something called projective geometry, and it's useful when you're doing computer vision and stuff like that. But for graphics, it just looks like a simple trick. We go from two-dimensional vector to a three-dimensional vector. X, y, and 1. X, y, and 1. If we take a matrix in this form and multiply it out, okay, so go A times X old, C times Y old, okay. Oh, and then the 1, and then what? 1, oh, E times 1. Oh, look at this. We're getting a translation here by this trick. Oh, so the whole reason we're doing this is we're able to incorporate translations into one transform matrix, okay? Because when we do these things, we are going to be putting transforms on transforms on transforms. This is how all computer graphics work. It's just one set of transforms. So let's look at how this might work, okay? Here's a matrix for scaling, okay? So I'm going to scale by X, scale by Y. I'm not going to move anything around, no rotations. Then I'm going to do translation, okay? So if I multiply this stuff out, I'll get something like the scaling X factor times X coordinate plus the translation, the scaling Y factor times the Y factor, okay? And at the end, I get a combined matrix that doesn't surprise us too much. It looks like what we were talking about before. Scale, okay, then translate. Different than translating than scale, okay? Now, if we're going to specify this in a computer language, the computer language of SVG or CSS, we're going to take this matrix and turn it into something that looks like this, okay? So we have all these variables. We don't bother with the last, putting in the 0, 0, 1. That's implied, okay? So let's see this in action, okay? So here is one of these SVG things. Here, I've got a rectangle. A rectangle, I've talked about all these different things. It's got a width, it's got a height, it's got a top left corner at this X, and this Y stuff. I filled it with pale green. Okay, that kind of makes sense. You know, and remember, we don't memorize all this stuff. We just copy and paste, and then we look up stuff if we want to add more cool things. Like we can have a stroke dash array and stuff like that. Now I'm going to take a copy of this, copy it here, then I'm going to apply a transform to it. A matrix. This, I said, is going to scale it by 2. Oh, that's right. 2, then 0, 0, then 2. So this is going to scale both the X and Y by 2. And then I'm going to move it over to the X 50 coordinate, add 50 to the X coordinate, and 100 to the Y coordinate. Okay? Similar for these other things. So let's go take a look. Okay? Taking a look. Okay, so I'm using a developer tool that comes built in to Firefox and Chrome. So here's our original rectangle. Okay? Our scaled and transformed rectangle is down here. Okay? Okay? We can see it's about twice the size, and we can see it's been moved over. Okay? The other rectangles we were looking at, we were working with, let's see, it's right here. Okay? And with that one, we shrunk it by half and moved it way over. And this final one here, okay, I took that one and I increase it by 5. I multiply it by 5 times. I scale it by 5, okay? And that's this translated version. I also applied some animation to it. That's something that you can do with Cascading Style Sheets. Okay? We didn't have to write any JavaScript code or anything for that. Okay? Close these tools and keep going. What about rotations? Rotations. You've seen this 2 by 2 submatrix here as a rotation matrix, okay? So I want to rotate and then translate, okay? So if I rotate, I apply that matrix first, then I apply the translation matrix, I get something that looks nice and simple. A rotation, okay, and a translation. Let's apply that, okay? How am I going to do that? Okay, I'm going to use a slightly different example. Okay, here's a rectangle, okay, kind of similar to one of the ones we used before. Now I'm going to rotate by 45 degrees, okay? And yes, I computed these things if you need to compute numbers, okay? There are other ways to do this, okay? But here's my cosine of the angle, my minus sine of the angle, my sine of the angle, and my cosine of the angle, okay? For this other one, I rotate by 80 degrees and then translate. Oh, and I'm going to apply an animation to this too. That I'm not showing you, that's a different course. Okay, matrix. Okay, so now we see the cosine, which is small because the angle is close to 90. Nice big sine here, sine, yep. Then we move it over. Let's see what that's going to look like. Oh, look at that. Okay, pretty cool. Now, observations. We don't always, and as programmers, don't want to have to work with matrix form directly all the time. There are a bunch of helper functions for us in CSS and SVG that create the matrix for us. We just tell them translate, or we give it rotate plus an angle, or we tell it scale and such like that. That will produce the matrix, okay? It will produce that matrix that we individually specified, each element. The reason why we might do this is because transforms are frequently combined. We do things like we'll translate it back to some place close to 0, rotate it, and then translate it some other place, okay? To do that, we need the full matrix version, okay? What do I mean by that? Each one of these commands will produce a matrix. The matrices all get multiplied together to produce the ultimate transform we want. One thing that's really important, transforms don't commute. Remember, matrices and the order of matrices? Order matters. Scaling and translating is different from translating and scaling. Try that example earlier, okay? When you debug this, you may be the greatest coder in the world, but if you forget these math concepts, you won't have a clue as to what's going on. So we need to think about what's going on with the math, okay? These are simple scaling things. Every coordinate gets multiplied, okay? Now, that's just a start, okay? To explore further, there's a nice free online book, Introduction to Computer Graphics, which will get you more of the computer sciencey stuff and will reinforce what you've seen about transformation matrices. If you want to get to three-dimensional stuff, 3JS is a library to help do that in JavaScript, okay? And Inkscape itself is a free open source vector drawing program, very, very elaborate, used by professionals to produce very elaborate drawings. It uses SVG as its fundamental file format, okay, which means you can then go and take something and animate it and apply transforms to all that stuff, okay? So what do I mean by three-dimensional? Okay. By three-dimensional, I mean, we're working in 3 dimensions. Okay, so we have our little robot here. Let's change his state to idle. Oops, I got my robot here. Okay. Every one of his joints, okay, gets a coordinate system, a 3-dimensional coordinate system. Everything he does, yeah, I'm talking to you, everything he does is based on moving angles between the various joints. Okay, this is known as rigging or skinning and such like that. When you put together an animated figure, you have bones and joints between them, and every one of these gets a coordinate system and a transformation that you specify. Okay, so this gets quite exciting. Okay, and it's quite a lot of fun, but you do need your math. All right, we'll talk to you later.